So what we've actually been doing is called approximate integration. And integration is basically just finding an area under the curve. So we had that definition of area, which is, all right, hold on, let me sketch something out for you real quick. So let's say I'm trying to find the area under a curve. It's just an arbitrary curve like this between A and B. So I'm trying to find that area. Then we defined that area as the limit as n approaches infinity of the sum of the areas of all the rectangles from I equals 1 to n. So f of xi delta x, right? All right, well, Leibniz, one of the fathers of calculus, decided sigma notation, that's not good enough. Even though sigma notation is a concise way to write a large sum, he decided, well, once we start adding up infinitely many rectangles, we should use a different notation. And here's what the notation is. It's called integral notation. He said, so once we're dealing with an infinite number or an infinite sum, I'm going to change the notation to be like this. You've probably seen this, right? That's called an integral. And he made it just an elongated S for sum, basically. And then what you do is you put your endpoints on the integral that you're trying to integrate from and to, so from A to B. So we call those our limits of integration. And then you're going to you put your function next. So I'm integrating f of x, and delta x starts out when we're doing approximate integration, delta x is a finite value, right? It's an actual width of a rectangle. But once we use infinitely many rectangles, how big is delta x? It's infinitely small, so it's no longer a finite value. So instead of delta x, which actually represents a finite value, we call it dx, which is an infinitely small change in x. So that's integral notation. We call this, the function that you're taking the integral of, we call it the integrand. And dx, like I said, is called a differential. And we're going to come across it more. I just wanted to show you today because you're going to see in your problem set the integral come up. But the integral is the exact area under the curve. And what we've been doing is using rectangles to approximate the area under the curve, right? All right. Let's do it. I'm not going to bother with any of these notes. I'm going to talk about the trapezoidal rule in a moment, but we've already actually been doing the midpoint rule. So I'm going to kind of do this in reverse. Let's start with the midpoint rule. Here, I'm going to do B first. So I'm going to use the midpoint rule, which means I'm using midpoints to find the heights of my rectangles, okay? And I'm going to use 5 subintervals to approximate the integral from 1 to 2 of 1 over x dx. So that's just the area under the curve, 1 over x, between 1 and 2. So this first one will be a little bit of a review. We've already been doing this. If you don't know what 1 over x is, it's just a hyperbola, but we can figure it out by plugging in 1. And when you plug in 1 to 1 over x, you get back 1. There's the first endpoint. And when you plug in 5 to 1 over x, no, I'm sorry, 2 to 1 over x, you get 1/2. So here's what my curve looks like on that interval. Something like that. All right, I just want to divide this up into 5 subintervals. So 1, 2, 3, 4, 5. All right, what's my delta x in this case? How wide is each subinterval? 1/5, 2 minus 1 over 5, or 1/5. Right, so what's the actual values of my indices then? My left endpoint's 1, or if you like, maybe this will make it easier. 1 is the same as 5 over 5, right? And then we just want to add 1/5 to get to the next index. So this is 6/5, 7/5, 8/5, 9/5, and then 2 is 10/5, right? Great. So M6 is what I'm looking for. No, M5. M5 is what I'm looking for. Each of these rectangles has the same base width, which is 1/5, so I can factor that out. And then all I want to do is add up the heights inside those parentheses, right? But I want to base the heights off of the midpoints. So I got to figure out the midpoints first. How do I figure out what's halfway between 5/5 and 6/5? Yeah, you just average them, right? So we're just going to add them and divide by 2. So 5/5 plus 6/5 divided by 2. 11/5 divided by 2. That's 11/5 times a half. That's 11/10. Everybody agree with that? All right. So the first midpoint I'm going to use is 11/10. I'm going to plug that into my function, and that'll give me this y value up here, which is going to be the height of that rectangle. What about the next one? We could add these and divide by 2. Kind of a pain. The other thing you could recognize is that if there's delta x between the indices, so from here to here is delta x, there's also delta x between the midpoints. So here to here is also delta x. So I could just add 1/5 to get to the next midpoint, right? Well, 1/5 is what? 2/10? 1/5 is 2/10. So if I add 2/10 to 11/10, what do I get? All right, and then what's the next one? 15/10, and then what's the next one? 17, and then 19, right? And that's what's going to get us our heights based off the midpoints. Great. To the calculator. I'm going to put my midpoints in list 1. Clear this out. All right, so what do I have? 11/10, 13/10, 15/10. 17/10, 19/10. Good. And then list 2, I'm going to program to be whatever my function is to give me the y value outputs from list 1. So my function is just 1 over x. So my list 2 is going to be 1 divided by list 1, right? And then these y values are now the heights of my rectangles. So all I want to do is add those up and multiply by my delta x, which is 1/5. All right. So again, we'll go to second list, go over to sum or math, choose sum, list 2, and then I'm going to multiply that by 1/5, which is our delta x. And then we'll round AP Calculus to 3 decimal places always when we have to approximate. So 3 decimal places, M6 is approximately 0.692. All right. Questions on that? So basically the same thing we've been doing, yeah? All right. So there's one more approximation rule you need to know. You know how to find approximate integrals using left endpoints, using right endpoints, using midpoints. And there's one more, and it's called the trapezoidal rule. And so basically what we do, let me resketch this diagram. What did you need, Vincent? All right. So we'll go 1, 2. I'm just sketching the same exact diagram. Still going to divide it into 5 subintervals. So 1, 2, 3, 4, and 5. Well, those don't look like they are the same width, but they are supposed to be. So here's how the trapezoidal rule works. What we're going to do is take the y values at every index, and we're going to connect them like this. And so what that makes is a trapezoid. Does everybody see that? Got the 2 parallel sides. Does anybody remember geometry enough to remember what the area of a trapezoid is? What?
Don't you just add? It's like base times height times base times height divided by 2.
Oh, you're close, Maisie. It's height divided by 2 times base 1 plus base 2, where the bases are the parallel sides. So these would be the bases. And the height in our case is that. Delta x is the height of the trapezoid. And so what you would end up with if you did that for each one, let's do this, just so I can develop the formula real quick for you. I'm going to label these indices as, this one's base 0, base 1, base 2, base 3, base 4, and base 5, okay? So if I wanted to add up the areas of all those trapezoids, I would do height divided by 2 times base 0 plus base 1. Plus, and then the next trapezoid would be what? Height divided by 2 times what? Talking about this one here. What 2 bases am I going to add? base 1 and 2. And then plus height divided by 2 times what two bases for the next one? 2 and 3. So the reason I'm doing this is to show you, notice what happens. And we would keep going like that, right? First of all, every one of those terms has the same height divided by 2 in it. So I could factor that out, right? So if I factor the height divided by 2 out to the front, then I'm going to have base 0 plus base 1 plus base 1 plus base 2 plus base 2 plus base 3 plus base 3 plus base 4, and then plus base 4 plus base 5. Whoops, not just plus 5, plus base 5. All right, so my point in this is notice that all the bases get used how many times? 2 except for the ends. They get used once, right? So this simplifies to height divided by 2 times base 0 plus 2 times base 1 plus 2 times base 2 plus 2 times base 3 plus 2 times base 4 plus base 5, right? And that's the trapezoidal rule. One other interesting thing about the trapezoidal rule is that it happens to just be the average of the right and left hand approximations. If you took those, added them together, and divided by 2, you literally get this. Because remember, the left-hand rule will start with base 0, but it won't use the last one. So the left-hand rule would use base 0 and base 1s through 4, but it wouldn't use the last endpoint. The right-hand rule starts with base 1 and ends at the last endpoint, so it doesn't use base 0. And when you average something, you add them together and divide by 2, which would give us the h over 2 at the beginning. So here's my final point. I'll call this T5, and T5 equals L5 plus R5 divided by 2. And that can be helpful on the AP exam if you can't remember how to do the trapezoidal rule. You can always just do in your calculator the left-hand approximation, the right-hand approximation, and then average the two values, okay? And I'll show you that right now. But we're going to do the actual trapezoidal rule in our calculator right now. All right. So we already know those actual values of the indices because we did it in the previous example. So let me just relabel those. What do we got here? 5/5, 6/5, 5/5, 6/5, 7/5, 8/5, 9/5, and then 2 is 10/5. And so for T5, what I want to do is do h over 2, or delta x over 2. Then we'll multiply that by f of x0 plus 2 f of x1 plus 2 f of x2, and so on until you get to the last endpoint. You only use that once, so f of x5, right? All right, so for us, delta x is 1 over 5 divided by 2. And I want to do f of 1 plus 2 times f of 6/5 plus 2 times f of 7/5. And I'll continue with that coefficient of 2 until I get to the last one, which is just going to be plus f of 2. Right? All right, 1/5 divided by 2 is 1/10. All right, so that's what I want to do. We're going to use my calculator to do the rest of this. So let's jump in here. Let's go into our lists. Let's clear them out. And now we actually want to enter in list 1 our indices. So our indices are 1 6/5, 7/5, 8/5, 9/5, and 2. All right. List 2, we want to get their corresponding y values. Their corresponding y values. These are going to be our bases of our trapezoids, right? So list 2, I'm going to program to be our function applied to list 1. Our function is 1 over x. So L2 I'm going to set equal to 1 over L1. All right, so those are the y values of the bases of my trapezoids. So here's something we have to do extra in the trapezoidal rule. Remember that we don't just want these y values. Every y value but the endpoints has to be multiplied by 2, right? So I'm going to take list 3 and I'm going to write those coefficients. I'm going to go 1, 2, 2, 2, 2, and 1. So those are the coefficients that I want. I need list 3 to be multiplied by list 2. Does that make sense? That's what I'm going to do. I'm going to program list 4 to go L3 times L2. Great. And so that is what I have inside my parentheses here. Those are those individual terms here. So what I have in list 4 is this. I've applied the coefficients. So I multiplied the coefficients times the y values. And now I just want to tell my calculator to complete the task. I want to tell it to add up list 4, and then I'm going to multiply by 1/10. That make sense? Let's do it. So this time I'm adding up list 4. Go to the main screen. Go to your list menu, to math, choose sum. I want to add up list 4. And then again, I want to multiply that by 1/10. All right, so I get 0.697 for T5. All right. Go ahead. Yeah, so list 2, let's go back here. List 2, these are just the y values at my indices, right? So these are, hold on. These are, what's in list 2? Are these values. Okay? But then remember, we used those heights, we used all the interior bases twice. They got multiplied by 2. And the outside edges only got used once. So this and this was only in there once. But every interior y value has to be multiplied by 2. So I set up my coefficients in list 3. 1, 2, 2, 2, 2, 2, 1. And then I multiplied list 3 by list 4. Or sorry, list 3 by list 2. And that gave me list 4, and that's what I want to add up. Now, what I said before was that really the trapezoidal rule is just the average of the right and left endpoints, and I'll show you that. So if I wanted to use a right endpoint approximation, I would not use my first height. I would not use that first y value. The right endpoint approximation would look like this. In this case, it should be an underestimate, right? So I would use this as my first height, second height, third height, fourth height, fifth height, right? So I can find my right endpoint approximation by, just taking out my first y value in list 2. Delete that. Then I can add them up and multiply by delta x. So if I go sum list 2, and then multiply by delta x, which is 1/5. This is my right endpoint approximation. Okay? I'm going to store that in a letter just so that I can easily average these in a minute. I'm going to store it in A. Great. So my right endpoint approximation is stored in A. My left endpoint approximation, let's go back. My left endpoint approximation, I would use the first y value, but I wouldn't use the last y value as my height, right? So I would use this, 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 and this as my height, but I would not use that last y value as the height of any rectangle. So in my calculator, if I go back in, stat edit, I'm just going to insert back my y value there, which was 1. And I'm going to delete off the last one because I'm not going to use it. And this should give me my left endpoint approximation now when I do sum list 2 times 1/5. And this one should be an overestimate, so we're going to expect it to be larger than that. And it is 0.745. I'll store that in B. All right, so my claim was that my trapezoidal approximation is just the average of left and right endpoints. So it should just be, no, let me undo that. No, I don't want an alpha lock. There we go. A plus B divided by 2, right? And there we go. We get that 0.697 that we got with our trapezoid. All right.
So is this the method that you would recommend on the AP exam?
It's whatever's fastest. Like, it's recommended that you know the trapezoidal rule, which is this, right? It's h over 2 times f of x0 plus 2f of x1 plus 2f of x2. But I just yeah, I don't know, Maisie. It's whichever you're most comfortable with. Like, if you feel like you can get comfortable with quickly doing left and right endpoint approximations, and you can get kind of fluent like I was with the calculator, like you know how to store values in letters, then yeah, I think this is just as fast as what we did where we had to like attach coefficients. Now here's the other thing. You are allowed to have programs on your calculator for the AP exam. And I have a Riemann, these are called Riemann sums. They're named after Bernard Riemann, the guy who made them up for approximating integrals. I have a Riemann sum program on my calculator that I can transfer to you, where it'll just ask you what's the right endpoint, what's the left endpoint, and how many subintervals do you want. And then it'll tell you left endpoint approximation, right endpoint approximation, midpoint approximation, trapezoid approximation. So if you are coming in person, I will transfer that program to you. And then I would just recommend using that. All right. I think I have an example I wanted you to try on your own. Oh, no. So just a couple notes about approximate integration. In any method, we get more accurate results when we use more rectangles and or trapezoids. So increased number of rectangles, better result. The errors in the left and right hand endpoint approximations are always opposite. One will overestimate, the other will underestimate. The trapezoidal and midpoint rules are much more accurate than endpoint approximations. So for our last example, T5 and M5 are both going to give better results than L5 or R5. And finally, trapezoid and midpoint rules, much like right and left endpoints, they're going to be opposite in sign. One is going to overestimate, the other will be an underestimate. And the last thing, the midpoint rule is the best. It's the best one you can do. The error will be about half that of the trapezoidal rule. All right. And that is it. You have a